on our best behavior. Any of you coming tomorrow night? Yeah, don't come. You're busy. You're students. That was a test. You all passed. If I see you there, I'll be disappointed. I'll be there. So what I have learned over the past 6 weeks, it is unclear if I am a good number theory teacher or not. And I assumed there would actually be a result by now, right? But one of the things that has happened is the population is heterogeneous with respect to number theory, which I did not expect. I expected there to be a diversity of programming backgrounds, a diversity of level of interest in cryptography. Unfortunately, there are a small number of students whom I did not detect early on who know a lot of number theory. And that meant that my initial measurements of how well I was teaching were extremely cooked, right? So it is possible you don't know as much number theory as I thought I have taught you for that reason, because my impression of education is there's functions of user time, which we'll think of as the time we spend in this class talking to each other. There's real time, which is, how many minutes since I started talking to you about number theory. And then I think there's separately some notion of system time, which is probably the time you spend in kernel mode while I am not there observing you. And some combination of those things are going to contribute to your degree of understanding of number theory. I worked through a few things on whiteboard with students in Salem today. They seem to understand it. I've been trying out new terminology. But I canceled the lab section in Salem today and did an additional lecture on number theory. That lecture will go up on YouTube. I'm not planning to deliver it to you necessarily, but there's one other lecture that I could also deliver in the same way. And that's a slightly different style of lecture. You have not seen me do this yet, but one of the things I do sometime is I live code the Quarto Markdown document that is documenting the mathematical things I am showing, and I show the equivalence between LaTeX and Python. To me, this is the correct way to teach formal mathematics since this summer, relatively new, right? Before that, I would have taught it in LaTeX. Anyways, I say that all to motivate that at any time, the right combination of questions today will prompt a switch into that form of instruction. And so if you have any specific questions, if you're like, hey, why does X or Y, I am happy and in fact eager to talk about those things, and we can go over them in exhaustive, excruciating detail, right? We can use most likely the combination of the Python language, ranges and asserts to write things that are very, very close to proofs in Python, and we can separately write the formal mathematical definitions in LaTeX. We can put all of this in a markdown document, and we can preserve it as a PDF or a website. And that means that we can have perfect disambiguity around whether this thing works. My impression of today, beginning with Fermat and beginning with RSA, is this stuff gets really squirrely really quick. I self-identify as someone that understands every atomic step of the RSA algorithm. Each component makes perfect sense to me when I look at it directly. And then when I think about it all at the same time, my brain instantly explodes and I'm incapable of reasoning about it. That makes it, and when I spoke about my excitement to teach the RSA algorithm, it is specifically a good algorithm, I think, to get good at thinking symbolically about complex systems. It is the perfect algorithm to do this. Public key encryption is just an important thing, and actually understanding it, I think, is good, right? I think separately we can claim, like, oh, like in a professional context, is it important to actually know how to understand how to implement public key cryptography? Like, maybe not, but if you can implement public key cryptography from spec, can't you implement anything from spec, right? So, like, I would argue that this is applied for that reason, that this is a problem set that teaches you to write code from a spec. So that's what I think. Since beginning this class, actually, I found what I think is a very good way to argue for the correctness of RSA that is called counting necklaces. This is a novel combinatorial proof. I'd never seen it before. Seems pretty cool, pretty intuitive, which is unusual for combinatorial proofs. Usually people do things with like dice or cards or something. This one looked pretty good. I have it in the slides today. So we're going to go through that, and what we're going to build up to is right at the end of this lecture, which does not have to take the 4 hours but can. At 4 minutes per slide, it will take the whole lecture. At the end of this lecture, you will understand how we can believe that the RSA public key crypto system works. And then the next lecture, which is called Euclid after the extended Euclidean algorithm, will tell you how to get this thing to run in a finite amount of time. Because otherwise the amount of time it takes to calculate some of the components of the public key crypto system is very, very high, right? Some of you have worked on long division with a 4096-bit integer. You are quite likely to have to either recurse or iterate 64 times, right? One for each of the blocks. Each one of those blocks on average takes 32 operations. So that's 64 times 32, which is 2 to the what? Some large number. 64 times 32 is 512. So you have to do 512 divisions per division, right? I think that's correct. And that seems much slower, right? So if my processor can do 1,000 divisions per second, now suddenly it takes a half second to do a division instead of an immeasurably small amount of time. We imagine now that we have to solve a problem by guess and check, right? We have to guess a number, perform a division, and see what the result is, this is one way to predict something called the multiplicative modular inverse, where you find what two numbers you multiply together to get one. There's a closed form way to do this. I will teach it next week, but if you imagine if you have to guess, now it costs 512 divisions per guess. And I have 2 to the 4096 numbers that I can guess. That takes literally forever, right? That is 512 times a number that is 1.5 times bigger than Google logarithmically, right? So if you turn that on, it will literally never finish. Every computer on Earth could start on that now and never finish, right? And it is unbelievably easy to do at 2 to the 16th because your computer can do that instantly. It's no problem. You don't even feel it at all. So RSA and C this week is not asking you to implement the algorithm that solves multiplicative modular inverse. That is the one difference. But once we know how to do that, next week we will be able to do this at scale. You don't have to know how to compute that value to know that it's useful. So this week we're going to motivate the usefulness of the multiplicative modular inverse, among other things. And then next week we're going to solve the performance problem. So we are going to do public key cryptography, Fermat's little theorem, and RSA. Public key cryptography is the description of the problem we are trying to solve. Fermat's little theorem is a seemingly unrelated mathematical result. I did not know it was related. I learned about RSA and Fermat's little theorem at separate points in my life, and I never perceived the connection between them. I'm going to argue for their connection because I have no other basis from which to argue that RSA works. You can try it and see that it works. This is relatively unconvincing because my impression when I first started using RSA is it really, really felt like it was a coincidence it worked every time. Right? And that was not a good feeling to have that in code, right? So I'm going to debug the mathematics here. And we're going to start this with public key cryptography. There are many ways to teach a class named cybersecurity. This class is named cybersecurity. It is not called cryptography. If it's offered next year, it might be offered under a different name, right? But specifically classes that are called cryptography or cybersecurity often do make some incorporation of historical events that are cybersecurity relevant. To me, the most relevant cybersecurity historical event in the United States is Edward Snowden collaborating with WikiLeaks and getting large amounts of information out of the NSA. Edward Snowden was caught in the classical sense, but is not in fact currently in US-based prisons, right? So this is someone that was able to move large amounts of classified data outside of classified realms without being stopped. This is anomalous. I use this as the motivating example for public key cryptography. It is not true that Snowden used classical public key cryptography. The algorithms Snowden used were extremely advanced. Snowden was able to do this because he was one of the most advanced cryptographic algorithmic researchers in the world at the time, right? And made considerations of a lot of other things, like, oh, what are the shapes of packets moving over the internet, right? Snowden had access, because of the information he was leaking, to how the NSA surveillance apparatus worked. So from knowing how the surveillance apparatus worked, he was able to make decisions about how to move information around without being detected by the surveillance apparatus, right? This is an extremely useful thing to leak, how leakers are caught, right? It's like, oh, yes. That's what I want to leak as well. But in its simplest form, we can think of this as a case of public key cryptography. The two characters that I'm going to refer to by name are the personalities associated with things. It is not my position that it is quite likely that either of these individuals were acting independently. Certainly, Snowden has, throughout the entire course of this process, was always in direct physical contact with his partner, who also seems unusually good at everything. Greenwald was part of a team affiliated with The Guardian and The Washington Post that contained other experienced journalists, right? So I'm going to use the last names of individuals, but I am referring to organizations, right? So the Snowden is an organization, even though there is an actual existing human named Edward Snowden. It seems unreasonable to complain, to expect that one individual could have done this in isolation, right? And so what's going on? Snowden, I think, started in Virginia, did the thing that all of the sort of like tech personalities did, where you like start a master's in computer science and you drop out halfway through. Don't do that. You know how like Bill Gates like dropped out of like Harvard? Zuckerberg dropped out of Harvard, right?
Yeah.
And we all know how well Facebook runs, so we know that was the right decision, right? Yeah, like they think they're so smart, right? They should have taken my classes. They would have not been bored. Okay, so Snowden is this character that likes fiddling around with computers, likes to install Linux for fun, that sort of thing, right? Not necessarily an academic interest in computer science, not someone that did research computing, right? The worst thing that can happen to someone happened to Snowden, which is Snowden had to get a real job, right? I've managed to evade this fate. Many of you will fail, right? And I'm sorry for that. We can't all become professors or Twitch streamers. And so Snowden got a job. Snowden liked computers. Just got a sort of entry-level gig at the NSA, apparently. And I think this was around the time stuff like Patriot Act was going through, things like that. So the United States, what I'm going to refer to as the surveillance state apparatus, was expanding very rapidly. And they were sort of taking any warm body at that time, right? So came in on a contract, sort of got slurped up into progressively higher echelons of the organization because he wasn't ludicrously incompetent like many people are when it comes to using computers, right? You all have, tried to install an antivirus software on someone else's computer and you're like, oh, you only use the downloads folder. I'm familiar with that because I also do that, right? So anyways, Snowden was basically a computing super user, not really a computer scientist, right? Working in Virginia, somehow mind controls his boss into stationing him in Hawaii at some point. Why do you get stationed in Hawaii? So Hawaii, essentially all internet traffic that goes in between the United States and this little continent I like to call Asia goes through Hawaii. And Hawaii is currently occupied by the United States federal government. So they put a data center there. And by all accounts, according to WikiLeaks, these documents, they kept a record of every single bit that went through Hawaii forever, and probably still do. That's a fairly large amount of information, right? That could explain, for example, everything we know about what people that live in the United States think about China, right? Like that is, the amount of information that is unbelievable, right? Anyways, while he was going through this process, Snowden, who I think is one of these sort of pseudo-like libertarian type characters, had some sort of crisis about consciousness, about knowing every single personal detail of every single human living in the United States for no reason, and decided that the best thing to do was contact some journalists that had been, specifically in his case, critical of the Iraq War. So there were not many, I don't know how much you read the news. My impression is that there are not very many journalists in the United States who are critical of U.S. bipartisan policy, right? It's relatively easy to find a journalist that is critical of one of the two major parties, relatively difficult to find someone that is universally critical. In fact, I couldn't name one, right? His impression was that Greenwald was one of these people, and I think Greenwald at this time was not even living in the United States. I think he's based in Brazil now, which is good, because I think they don't have an extradition agreement with the United States, right? So all this stuff is going on, right? Snowden uses a contractor's badge that they left lying around, slurps down large amounts of information even he wasn't supposed to access to, despite having very high clearance, No one at the NSA noticed that someone that was currently on vacation was downloading terabytes of data. Pretty interesting. I think they would notice that now, and in fact, they caught the next person that tried to do this. And doesn't have any way to move that data anywhere because every single cable going in and out of Hawaii is monitored, right? So, and he knows this. So, somehow, Snowden has to communicate with someone on the mainland at this time, somewhere in the Americas, and needs to have like a reason for doing this, right? And so this is the invention, or the motivating example of public key cryptography. If you know someone is monitoring every single thing you're doing, can you still communicate a secret? And the answer is yes, you can. You cannot hide that you are communicating a secret, but you can hide what you are communicating. So maybe Snowden was just making a lot of very, very embarrassing purchases on Steam, right? Like maybe this was a completely reasonable thing to do, right? Maybe Snowden was really into Monster Hunter Wilds, right? And doesn't want anyone to know that. This is, oh, I thought I corrected that. This is the textbook for the class that we're not really following, but is, interesting to study. A key exchange protocol, which we denote as P, is a pair of probabilistic machines. What does that mean? It means they're capable of behaving randomly. There is randomization in here. Randomization is going to be a problem for us. We haven't talked about randomization yet. I have a little description on the problem set, how to deal with this. I consider random number generation outside of the scope of this course, so I'm going to tell you one of the standards for doing it and then just tell you to do that. Here's a pop quiz question. Are you allowed to ever use any of the code you wrote in this course for anything under any circumstances at all ever? No. No. Are you even allowed to look at it? Should we even think about it? Should there be any evidence this course existed at all? No. The only thing that should change is our consciousness. Yes. We don't want to be caught doing this course, right? This course is suspicious. Okay. So these two machines that are capable of truly random behavior, which... So we're actually portraying a character right now, right? The character, assistant professor of computer science, Calvin Deutschmeyer. I'm so sad. So I'm worried someday I'm going to get tenure and have to rebrand, right? I've been saying assistant professor for years. I'll have to change like all of my handles on social media, right? So these probabilistic machines are sending messages to each other, and what the messages say, we'll get to that later, right? At some point, they no longer have to send messages to each other because some secret information has been communicated. Maybe they keep sending messages so it looks more or less suspicious, right? That is up to you. This is the introduction of the term terminate or halt. If you want to know more about that, take my theory of computing class, which is posted. We want to, I think of them as geographically separated, but they're logically separated. Logically separated devices to hold the same, essentially numerical value. It is reasonable to think of anything in a computer as a numerical value, and that value is k. And then there is a series of messages that are exchanged between them. This is the formal definition of a public key crypto system. I don't worry about this too much. Do you all know what random variables are from any of your other classes? You do. You knew what congruence was. The undergrads were roasting me for congruence. Apparently they were talking to me about me to the math professors without telling me. They're like, Calvin's saying equivalence.
Well, I mean, they're equivalent and congruent, but they're not equal.
Yeah. Yeah. Well, we think that you should not, it seems inappropriate to use equivalence unless you're referring to a relationship that its significance is that it is an equivalence relationship. And we do not care that two numbers are equivalent under, I don't know. So we are generating what amounts to random bits that satisfy some constraint. We have this eavesdropping adversary that by convention we refer to as E, which is also, as we all know, equal to MC squared, right? And this eavesdropping adversary can see these bits that are random even though they are laden with information and not be able to come to any conclusion about what information is being shared. But they can determine that some information is being shared, right? There was a recent bill before one of the bodies of the US Congress to make cryptography illegal, which is like not like a super well-formed thing, right? So there has been pushes from time to time to just like make it illegal to encrypt anything at all, which makes it very hard to do like online credit card transactions is usually what comes out. So like you imagine if you're Amazon and you have $4 trillion, right? You can probably prevent the US Congress from outlawing cryptography, right? So in some sense, you're always protected from using cryptography under the current global economic, arrangement, right? But there are always, at all times, there are various factions that are conspiring to make cryptography suspicious in its own right. I read a legal brief some number of years ago that it was held in suspicion that someone didn't have a Facebook account, right? It's like, oh, you're too private. That alone is cause for suspicion to be guilty of some crime, right? How's this working in practice? Who loves hard drives? I love hard drives. They rotate at 4,800 RPM. They have a combined magnet laser that can read whether a magnet is positive or negative. These magnets are like very, very close to, they're probably not nanoscale, they're probably like 15 nanometers or something. Anyways, and each one of those bits can contain 1/2 to the like 400,000th or something of Monster Hunter wilds, right?
You got an upgraded SSD?
I have an SSD, but in like 2007 or whenever this was. No, it wasn't 2000, it was 2014. Most of the data centers were still running on hard drives then, yeah. And my first job in undergrad was optimizing hard drives, and it was a much, much cooler research problem than optimizing the SSDs, because the way you optimize SSDs is you get the chemists to make a slightly better goop before they print the chip, right? And the way you optimize hard drives is you make motors that go really, really fast, right? And like one of those things is funner than the others, right? Going fast is funner than goop. We can all understand that, right? And apparently, as far as I know, some of the data centers are also still using tape, which is, yeah. So I think I personally keep all of my slide decks on VHS, right? That's how I store them. Okay, so Snowden can't transmit anything in plain text. It's probably inherently suspicious to even transmit the amount of information Snowden wants to transmit. It would be extremely suspicious, and in fact was one of the things that raised suspicion, if Snowden were to reach out to any journalist at any time for any reason, right? So I think Snowden reached out over, I believe, literally Twitter DMs, which how else would you get in touch with a journalist, right? That's the only way. No one's ever found another way. They don't check their email, right? And I think like one of the benefits is like Twitter DMs were like incrementally slower to monitor than email at that time, right? So it bought him 14 days, which is about how many he needed, right? So somehow you've got hard drives, terabytes. I don't remember how big the original leak was. I think it is double-digit, but not triple-digit terabytes, right? So we're moving large amounts of information. Not a difficult amount of information to move, right, if you have been one of the most advanced data center workers in the United States for a decade, right? So I think like I can figure out how to move several terabytes of information over the internet pretty quickly, and I'm nowhere close to people that work at data centers full time. This is so simple to them. They know so many tricks to do this. They're like, oh, plug in this thing here, use this protocol, all of that, right? He knew all of the optimizations. You know who didn't know the optimizations? Glenn Greenwald, right? So someone had to teach him all of this stuff. So Snowden contacts, the organization known as Snowden contacts the organization known as Greenwald. My understanding is the way this has been presented to the public is they used a series of increasingly more secure methods to communicate over time. So the initial thing was just, please run this program and post the results in some place that I can find it, and that was generating the public key, which we're going to talk about. And that was the last they ever used public keys. They used significantly more advanced applications after that. But this is a relatively unsuspicious thing to do. It is suspicious for someone that works at a data center with security clearance to ask someone to do this, right? So really someone else should have asked Snowden to do this, or should have asked Greenwald to do this. I speak to journalists from time to time. I always ask them to have some form of secure drop or something. They never listen to me. And that's fine, that's their business, right? I have leaked like things that are not going to get me in prison, but I didn't want to be affiliated with before. It's usually quite simple, right? But I didn't have to go through all the steps. Because like anything I share with the press is something that like, oh, it might be personally embarrassing and one of my friends at work might not like me. And this is, you go to jail for the rest of your life, right? So like different scopes of security. But because there are people that are sharing things on the condition of anonymity with the press at all times, and because you don't know who's snooping on your internet transaction, it is not inherently suspicious to be encrypting things on your device, right? That is not cause for suspicion in its own. I do think, and everyone has reasoned this, that like if anyone who works for the NSA starts encrypting large amounts of data, that is borderline criminal already, right? So you are not allowed to have privacy if you work for the NSA anymore. Were any of you planning on working for the NSA? Yeah, right, so just get your affairs in order first, right? You might want to become a VTuber, so that way you always have plausible deniability, right?
Already 3 steps ahead.
You're already 3 steps in.
30 separate YouTube accounts.
There you go. We're practically there, right? Just get up to 5 and then you're ready. Because you have the one for the VODs, then you have the raw footage, and then you have the video essays, of course.
Oh, you're also trying to get in the NSA.
Yeah. Well, I mean, you know, the money's good, right? So this did raise alarm bells, but not in time from the position of the NSA. Apparently, Glenn Greenwald, who has a personality, which we all love that, one of my favorite characters, really hated every single second of this process and couldn't figure out why someone wanted him, a journalist, to use a computer, the things that nerds use, right? So there's lots of funny interactions about like, I'm not reading that email. And so when I say the organization representing Greenwald, apparently someone that like worked with Greenwald looked at this and was like, that's probably the most valuable email you've ever gotten in your life. And in fact was. And so I guess someone else who I think maybe has actually protected their anonymity did all of this on Greenwald's behalf, and they gave him credit for it, which is exactly how you want to do things. You want the people with personalities to be in public, and then you want the people that know how to use computers to not have to talk on camera, right? Which is why this camera is turned off. So what's Greenwald do? A little bit of this thing I like to call computer science, right? Using a computer to compute values that are determined through a naturalistic process to have certain properties, right? So Greenwald enrolled in my class. At that time, I was teaching undergraduate networks and systems at the University of Chicago as a TA. And I'm assuming one of the students was Glenn Greenwald. I don't know if that's true for sure. He wasn't enrolled at the time, but it still could have happened, right? What are the numerical values? There's essentially 3 of them that matters. We tend to keep track of more than 3 of them, but there's 3 values. I call them the encryptor, the decryptor, and N, the modular base. N is the maximum size of message. The encryptor is the thing that everyone can see, and the decryptor is the thing that no one else can see ever, no matter what. The encryptor is the public key, and Glenn Greenwald, I believe, puts this in his Twitter bio, where everyone in the world could see it, and helpfully did exactly what you're supposed to do when you see a journalist doing this, which is no matter who you are, you start sending that journalist things so that there is a flood of network traffic that obscures whoever the individual is that is going to send something, right? So I did my part. I sent Glenn Greenwald my entire YouTube comment history, which was full of absolute bangers, and I sent them as images, so it took up more space, right? That's not true, but it would be funny if I had, right? I was actually an illiterate 20-something and had no idea what was going on in the world in 2013. I learned about Edward Snowden when I took my first job at the faceless evil multinational corporation Lockheed Martin, and they had wanted dead or alive Edward Snowden posters on every single door, which was a little bit horrifying. Anyways, who here wants to work for the faceless evil multinational corporation Lockheed Martin? That's right, and they did not. Okay, we're going to see an example of such technology on the next slide. I love this, so I embedded this as an iframe. We all know what iframes are, right? They stand for invulnerability frames, and they're used in Monster Hunter Wilds to prevent you from taking damage from attacks that would have otherwise been incident with your hitbox, right? As we know, iframes don't work very well, so we're going to click this link instead. This is the Intercept. The Intercept was founded by Glenn Greenwald, Jeremy Scahill, and someone who is not a public figure based on like some libertarian millionaire or billionaire, there's like a lot of people in Silicon Valley with more money than sense, right? That's where Bitcoin comes from. And The Intercept does its best to support whistleblowers, and they did a very, very bad job not too long ago, and now no one whistleblows to them anymore, but they're still trying because they should, right? And it is good that they are trying and bad that they failed, and still probably a public service that they exist, right? You are, I think, not supposed to click on these links on the open internet. You're supposed to use Tor browser. Tor browser was something that it was taught in my second semester undergraduate networks course, so that is slightly out of scope for the first course, but it's relatively uncomplicated. Essentially, the way this works is all of your web packets are put as the content of a package to another destination, and then there's a network of people that participate in this broad Tor network that basically obscures what traffic is going where. It was widely regarded to be secure until someone became pretty sure that the NSA was controlling more than half the nodes in it, and it was a honeypot. So, anyways, we don't know for sure. It's the best available technology.
Professor?
Yes?
A question. Can you use a proxy to achieve the same effect, or no? Is there something?
This is a proxy to the nth power.
Gotcha.
Yeah, I would assume a proxy is insufficient. It is generally considered that an arbitrary number of proxies is, in fact, still insufficient. I believe, right, probably if you go to this website, it will tell you what to actually do, which is presumably significantly more involved than this. If you do not need this level of security, you can just send them tips. And don't email. They know, USPS. I personally wouldn't be based in New York City if I were trying to be secret. But, I think there's like really good bagels there. That's what I've heard. Anyone from New York City, New York State? Anyone from Albany? 50 miles on the Erie Canal. We've hauled some barges in our day. No, okay, all right. Yeah, I mean.
And the steam in hand.
I love a steam. There's no way that's true.
Albany, not New York City.
Oh, okay. Okay, I'm with it. I'm back. I'm locked in. Wait, that's what I linked? I just linked Google? That's probably not what I meant to do. Anyways, this is Reality Winner.
Winner for the best name of any whistleblower.
Right, like there's no way Reality Winner is Reality Winner's name, right?
Reality Winner is the name that she was given at birth.
I'm just not going to believe that, sorry. Like, there's no amount of evidence that will convince me of that.
It says on Wikipedia. You
Yeah.
just need the slide somewhere in this deck that Wikipedia is over, so you should listen to your parent.
Yeah, that's true. Anyways, don't work for the NSA. He'll go to prison. Something that I think, like, there's more to life than game theory, right? But, like, it seems like every vaguely competent person with a conscience that works at the NSA either quits or goes to prison. And that's, like, whatever, right? But, like, say you're a United States congressperson. Would that not make you stressed out about the quality of work the NSA is doing at some point, right? Like, I think, like, so say you only care about surveilling private citizens regardless of whether it's ethical or not, right? This is still causing you problems, right? Like, even if you don't have a conscience, other people do. I have not seen that much analysis about this. I mostly think about this in the context of Google, where everyone I know that works at Google gets really sketched out after a while and either tries to change something and gets fired or quits on their own. And it also seems to me like Google gets slightly worse every year. And I don't know what they're doing that's worth everyone there quitting, right? Like, that seems very odd to me. It just doesn't seem to make business sense. It's not, like, inherently suspicious. Like, there's nothing Google can do that's, like, secret. Like, we know where the physical data centers are and, like, millions of people work for them or something, right? It's just, like, why do they do sketchy stuff all the time? You have to lose money doing that. Thank you for coming to my data ethics class. Okay, so what's step 2? Remember Glenn Greenwald ran the program on his computer that generated the public key? which I'm going to refer to as E, the encryptor, right? He also keeps a private key secure. I'm not going to talk too much about private keys in this class. The Bitcoin people are super into this. They tend to use, they like to stamp numbers into metal. So like you take a washer and you hit something that's shaped like a hex character, so 0 through F, and you stamp that into the washer, and then you store the washers on a screw, and you keep this on your person at all times or something, right? And this is perceived as secure to them because they've never been mugged, I guess. I don't know exactly what the intercept did, but I do know there was a security breach there, and it did not incur within their computing systems, right? So they seem invulnerable to cyber attack because obviously they are going to be cyber attacked, right? So I think whatever they're doing is they probably do have hard drives, probably not SSDs, I think. And I think these hard drives are air-gapped, so they have no physical connection to the internet, and they are probably inside a secured facility with good locks and maybe full-time security staff or something. I'm guessing they're not invulnerable to land invasion by a military, but I'm guessing it is if the FBI were to show up with a warrant, I'm assuming they have doors that are secure enough that in theory the FBI cannot get through them before the drives are destroyed, right? Something like that. And why do you do this? Because there's potentially people that go to prison forever if information on those drives gets out, right? So you have to invest some amount of energy and effort into making sure that you can destroy enough evidence that it's hard to incarcerate someone until the end of time. I don't know the exact best practices for doing this, but one of the things I always said is if you can buy a certain amount of time before the FBI gets to your physical computing device, you can make it very, very hard to recover data from it. And in practice, the way to do this is you write over the old data a lot of times, right? A couple hundred times, then it's probably gone, right? Okay, I'm gonna take another bite of pizza. How's everyone doing tonight? Do you all remember Snowden being in the news?
Yeah.
Oh. It's been a long time now, right? Here's another thing that's anomalous to me, right? Virtually everything that was leaked by Snowden has now been just published, which is crazy, right? They're oh yeah, all that stuff that we were going to arrest him for is true and also protected under the Freedom of Information Act. I was that's interesting, right? And yeah, there's been no successful whistleblowers since then. And presumably if there's a public admission of the things that sketch Snowden out, there are worse things happening secretly. I don't know what those worst things would be, right? Because it seemed like the worst things possible were happening already. So I like to imagine that. I like to hope that at the NSA they have a complete copy of me that runs on an LLM and posts the exact same tweets, right? And they'll know there's something wrong if I ever post a different tweet than the model of me. Someone's taken Calvin. If a journalist has a public key, you should make some effort to transmit them some information, and the information can say, you don't have to read this. I was just hoping you're having a nice day. I always encourage people to do this. There's relatively few people that have the technical bandwidth to actually secure or transmit relatively secure information, and you are all in that population now. I've taught you how to use the Linux command line and all this other stuff, right? Send journalist stuff all the time.
A little bit of cryptography, just going back a bit, you talked about AV and there's an adversary that's looking at you. And the idea is that they're monitoring you. So you have to send something that's encrypted, but they know there's a transmission. But they don't know what it is. Is there some cryptographic algorithm or some kind of cryptography that takes that message and just makes it look nonchalant? Like ordinary traffic, and they don't know it's something secretive being passed?
What's demography? Well, that would be when you hide a message in another larger message. Like if you had an image that when you fed into a program had a secret thing.
Sure, something like that.
Yeah, there's a lot of stuff like that. My impression is I don't trust a lot of it, right? Okay. But there are ways you can prove that no one can determine this image hasn't been tampered with unless they have the key on the other end, right? So the common use case for this is I physically go to a location and leave my laptop there by accident, and it has all of the image files on it that can only be encrypted by the thing I know the other person has, right? Yeah. Yeah. Ooh, should we do monkey type?
Huh?
Should we do monkey type? Typing really fast mentioned? Okay, let's do it. All right, it's time for a stretch break. We're going to stretch out our fingers. Please join me in going to monkeytype.com.
We should do monkey. They have a C, I'm pretty sure.
They have C monkey type. I'll do whatever you want. I do it for the fans, right?
They have a bunch of programming languages listed for the languages, which I find very funny.
There's languages on here?
Yeah, you can do French.
No, I can't.
Well, if you wanted to, you can do French.
There you go. Where do I click? Why do you know this? I'm doing English.
Okay.
Oh dear. So I started doing this with my students because I watched a lot of people debugging code that didn't seem like they could type. So I've tried to gamify typing. So I keep this a pretty big secret, but some of you may have inferred that I'm a gamer. And I learned to type when I was under 18 and didn't want to turn on my microphone, and I was a raid leader for a guild in World of Warcraft. And in World of Warcraft, there's something called the internal global cooldown, I think, the IGCD. And so when you cast a spell in World of Warcraft, you can't make any inputs for 1.5 seconds. So if you can type a complete thought in 1.5 seconds, then it doesn't matter that you don't have a microphone, right? Because every 1.5 seconds you can take a break, right? So that's how I learned to type. And I think that's like a huge part of the reason I can program. Like being able to think or like do complex problem solving. Like to me, I don't perceive like implementing RSA as any different than any other game, right? Or puzzle or something. Like I solve Rubik's Cubes, I do crossword puzzles, I play Monster Hunter Wilds. There is no cognitive difference in any of these things for me. I design course materials the same way. The other thing I've gamified is suffering. I love pain, so I do cardio, right? And so I think probably something that is going on with everyone to some degree, and I felt it there when I tried to go as fast as I could and started making mistakes, is we should not underestimate how much cognitive load typing is imposing on us and the degree to which we can train that away completely separately from training ourselves to actually do computer science, right? So I've really come around to the conclusion that like, if you want to systematically approach being really good at something, you should find ways to gain marginal advantages around the periphery that don't sort of overwhelm your other cognitive load, right? So I can only do automata theory so many hours a day before I get exhausted and then I can't think anymore. But after I do the maximum amount of automata theory or C development or something, after I'm too tired to do C development, I can do Python for a while. And after I'm too tired to do Python, I can do really high level language like Java, right? And then after that, I can still type, you know? So I've sort of tried to approach my development as a scientist in this way, and I found it rewarding. You see this a little bit where, to me, there was a intentional build up of skills you can do at different fatigue levels, beginning with Podman. So Podman containers, I think, are relatively easy to work with and fiddle around with, and you can probably do that after your brain's completely melted from writing C. You can probably still run the testers and still learn a bit of Bash, right? And then typing is sort of like the furthest out thing. And then like my other story about typing that I think this is relevant. A while ago, I got an email from someone who is not a professor at Willamette that said, hey, we know you're the computer science department. There's some computer science classes we need you to teach because they're required for like this other degree program, which was like some teaching degree program. They're like, yeah. They're like, we need you to teach people how to use Google Office or whatever that's called, the Google Suite, like Google Docs and stuff, right? And I said, that sounds like typing, and you should have the English department teach that because they're the experts of typing. And that person never reached out to me ever again. I completely solved the problem by being unbelievably mean for no reason. But I think like telling someone with an English degree that they have a typing degree is like a great thing to do, and it's really a good way to not have friends. So I only have enemies now. The dean and the provost both have English PhDs, and you can tell, I think. Like, why am I recording this? Okay. It's that simple. Moving on.
I really understand why you said we don't want to be caught doing this for us.
There is nothing I do that's not unbelievably suspicious. I'm like, so if you were to happen to like intentionally get a job at the NSA to become a whistleblower, right? Yeah.
Speaking of gaming,
Yes.
I find it so odd that the video game industry is sort of congealed around like Montreal, which it makes sense for tax reasons, but the Canadian standard keyboard layout does not have any sort of brackets, even if you do shift. It only has parentheses. On Mac, you have to use Option to get brackets.
You play with mouse and keyboard?
I play with mouse and keyboard.
Well, you said keyboard, right?
Yeah.
No, we use Xbox controllers. This is North America.
How do I type curly brace on Xbox controller?
Probably pull up an on. Yeah, there you go. Someone knows. Thank you, Jade. There was a correct answer to that question. Yeah. I was trying to figure out if I could write C code on an Xbox controller, so I had better posture when I held the controller. That's one of the reasons I started gaming, because I used to read books, and it was bad for my back, right? That's why I stopped.
You can't call yourself a programmer or a gamer until you can do all inputs with voice to text while having your eyes completely closed.
I just say the Vim commands.
Yeah.
J, good. Okay. Little known fact, public key cryptography, according to the people that made it, is accessible to people that are non-computing specialized journalists. This is not true. None of them could do it right. They all like had some friend that like came over to their house who like downloaded Linux for fun and liked imaging drives and did it for them, right? What I think is actually true of public key cryptography is someone with like a basic computing background and not a doctorate in cryptography can do it, right? Which is true. I am pretty sure I could leak sensitive information if I had enough time to prepare, right? And one of the benefits of this is like all this stuff is like documented and people have done it before and you can look it up and it's like not inherently suspicious for someone into computers to be like into RSA cryptography, right? And I think probably this is one of the things that like really helped Snowden. Like it would not have been at all suspicious if Snowden was looking into like every single cryptographic algorithm in the world because he like worked for the NSA doing code breaking stuff, right? Like it was kind of his job, right? And like it's not suspicious if I'm a CS professor and I'm like looking up cryptography, right? That's like sort of baked in. I'm supposed to be doing that. And I think that this will be true for any of you. You're like, oh no, I'm a back-end, front-end web software engineer, or whatever the job titles are. I was looking at job titles today. Some of those things seem pretty made up. A bunch of them had production in the name. And yeah, like, so you like screw around with keeping user data secure all the time, right? Like, yeah, you should know how algorithms work. Okay, so anyways, that's public key cryptography. I post something on my Twitter bio. Edward Snowden encrypts a package. The package is not the secret information he's trying to get to me. It's descriptions for how we do the next more secure level of encryption, right? That's all there is to it. I think it's important to be aware of what is and isn't possible to transmit over the open internet without suspicion, right? And there are other things that are interesting, specifically about Snowden's story, about like the way he got out of the country is he like pre-approved a vacation to Hong Kong and then like overstayed a visa or something, and like it took the US government a while to notice he wasn't on the plane back because he'd had a return plane ticket that he just didn't take and stuff. Like those things are clever and you should do them in general, right? And that form of cleverness happens all the time. So for a while there was a website that was getting people really low fares on flights by booking connections, then you leave the airport at one of the connections. Yeah, right. And so like, yeah, just like be clever all the time. And sometimes it matters a lot and sometimes it's just like cool and fun. What's this slide say? So I'm thinking of a word. The word is hello. If I put the word hello in a computer, is it also a number? Yes. How can I figure out what number it is? I think it's time to open our most beloved operating system. I put in the request to WITS to do Fedora Atomic Desktop, and they said, "What's that?" "Do you want to run that in VirtualBox?" they said. I was like, "No, I do not."
You could ask them for just like a Raspberry Pi.
I asked them for one that had an NVIDIA chip in it. I was like, does this Raspberry Pi have an NVIDIA GPU? Is a question I should ask more often. What's in here? Let's see. Okay, we got... this is what we did in the other class today. Cool. Hope none of that stuff was important. One of my favorite things I learned about Linux is that when you delete things, they're actually gone. But they're like not that gone, right? Because there's always some command line utility that can bring them back from the dead, right? So like, there's still recycle bin, it's just like on hard mode, right? Okay. What are we doing? We're doing hello number, which we'll abbreviate as hellnum. Okay. What's the first thing we always do when we're in Vimothy? We thank God we're not using NeoVim. Okay, right, so that's the first thing we do, right? Okay, and then the second thing we do is we press I to get into insert mode.
NeoVim is 6 characters though.
I'm listening. Maybe the string we should store is NeoVim. That'd be fun. That'd be meta, right? Okay, I'm going to use standard int.h because, no, I'm not. How do you, we just did monkey type, right? I think I'm making my point here. Int main. Okay, so let's take a string, and we're going to say the string is a character star. It's the location of a character, and it's followed by a series of characters, the last one of which is 0. I am just going to place my faith in GCC that it is going to give me enough space for the string I'm going to put here. That faith is misplaced, but it is out of scope to do anything else right now. Just kidding. I'm going to say I get 8 characters. Okay. S8 equals NeoVim. I asked for 8 characters worth of space. I provided a 6-character string. There is a hidden implicit 7th character, the null terminator, 0, right? So that is 7 characters of information. Should I make this bigger? How visible is that? Can you see that okay? Okay. I realized I couldn't see it, so. So that fits well. There is one unused bit, or there's one unused byte, but I'm not going to charge you for that one. That one's on the house, right? Because you might feel very strongly about NeoVim and want to go say, NeoVim, right? So lucky us, there's a built-in function in here. We can just print this thing out as a string, right? This is great. That's all there is to it, right? And I don't know why I still called this hellnum. What is my computer doing? Okay, there we go. It's tired. NeoVim. And it occurs to me at this time that we should have put a new line here. Okay. I forgot to press I. All right, did they teach you to use NeoVim in undergrad, or did you do that because you're a lifestylist?
They didn't teach me to do NeoVim in grad either.
Well, I know we didn't teach you in grad. I am a firm. I don't even know why I like Vim. I just decided to make it my entire personality, right? Do I have Emacs? I'll think about it. All the Rust people are switching to this one written in Rust that's like the same thing, because the Rust people only use things written in Rust for some reason. Like they started re-implementing pandas in Rust. It's like polars, look it up, because it has to end in RS, right? It's like, It's like, we get it, you like Rust. Go work for Mozilla. Okay. Okay, so there's NeoVim. And so this may mistakenly appear not to be a number to us. But we shouldn't trust our instincts, right? We're humans. We don't understand how computers work. And in fact, I'm going to reveal that this is in fact a number. I am going to create a uint 64t. And I am going to call it alias. I'm actually going to make this the location of a uint 64t. And I'm going to set that location to be the same location as s. Now, I think if I were to compile this right now, GCC would be very unhappy with me. Ooh, not allowed, because it is an incompatible pointer type. But I'm going to use my godlike powers. Oh, was that annoying the whole time?
I couldn't see what you were typing.
That's, I'm sorry. So what is S? Should we print out S? Should we look at S? Do you all know what S is? It's a 64-bit number, right? The 64-bit number represents a location in my physical hard drive that is being emulated on a solid-state drive in real space, even though in my mind I know it's a hard disk drive, right? And so this is just someone's address. It could be an email address. It could be a home address. It could be your favorite number. It's probably going to be a multiple of 16, right? And so this S up here refers to the location of this N, but it's just some number. They're all numbers. Really, they're not even numbers. Really, it's just bits, right? So I can say that this location, which is bits representing some location, is not actually representing the location of a character. It's actually representing the location of a uint 64t. And we can also, we'll make this easier on us. We're also just going to print %LD probably for a long decimal, and we're just going to print the number. I can't in good consciousness use decimal in this class, I'm sorry. Okay. We're going to give ourselves a new line at the end of that, and we're going to print alias. We should realize at this point in time that, like, hey, wait, can't I just not have this local variable here? Yes, of course, yeah. We had to motivate the example. Right? How did I get rid of the semicolon there? Where's my cursor? Is it still called the cursor in Vim? Let's see, long unsigned. Oh, I have to dereference. Okay. I have to say star. My compiler is very slow today. So in fact, NeoVim is just that number, right? And what number is that? Well, I'm going to examine this a little bit. Is that how that works? Is it ORed? So n is 110 in UTF-8, which is 6e in hex, which is probably that 6e right there. Remember endianness? We've inverted the ordering. I'm guessing that means that E is 6.5. Lucky guess, right? 6.5, probably 6F. Well, O is what? The letter immediately after N, LMNOP. So O is 1 more than N. We already know what N is. It's 6E. If you add 1 to E, you get F. So that's 6F represents O. Let's see, we have 6F, and then we have 7.6. If O is 6F, then P is 7.0, Q is 7.1, R is 7.2, and I think V is 7.6, right? I'm not going to go through the alphabet. Doing the alphabet in front of students is dangerous, right? I often leave out many letters. I is a few letters after E, unless it's before C. right? Because then it's not, yeah, okay. And then we've got m here, which is right after n, or before? Which one of these is n, m? It's this, I'm lost.
60.
It's 60, it's right there. Oh, because n is 6e, right? What's that a? The non-printing character has a very small value. New lines have a very low number in UTF-8, right? So it doesn't have a leading 0, so it just appears as an A. So in fact, everything we put in our physical devices in some way can be represented numerically. Why is this? Are they all really numbers? No, really they are all bits, right? But commonly we think of the bits as the numbers. That's the easiest, probably most recognizable representation of them. And equivalently, you can think of them as strings, right? They are, in fact, bit strings, right? It is a language. It is a language with 2 characters in it. So we can jam anything into a number that we want. Now, I stored neovim in one 64-bit integer. In 496T, you have 64 64-bit integers, so you can store relatively large strings. You can store Edward Snowden is contacting Glenn Greenwald and would very much like the Greenwald organization to set up a secure drop page. If you don't know how to do that, ask your local computer science professor who teaches evening classes at Willamette University's Graduate Professional Center on Thursdays from 6 to 10 p.m. Even though I noticed the students tend to flag a little bit around 9:30, right? So they should probably drink more caffeine. Who loves math? Look, it's math. That's real math. You can tell it's real math because there's a there exists, right? Existential qualifier. What are the values here that we're working with? There exists an encryptor, the public key, a decryptor, the private key, P and Q, 2 primes, mind your P's and Q's, right? These are elements of the natural numbers. That means that they are positive integers. They have no decimal component. There exists these 4 numbers such that for all m in the natural numbers, that's false. It's actually for all m smaller than PQ, but I'm allowed to make mistakes, right? I was not elected pope. I threw my hat in the ring. I said I'm infallible. Everything I say is the word of God. And the Catholics said, we've seen your post on Twitter, and they threw me out, right? Okay, so we take this message. This message is perhaps neovim, right? We raise it to the power e. What does that mean? We multiply it by itself a bunch of times. This multiplying itself by itself a bunch of times is an important thing to remember because we're going to come back to that. It's going to cause us lots of problems, how we have to think about that multiplication, right? This thing, m to the power e, is our ciphertext. That is the information that contains the secret. It is not the same as the secret, but anyone who knows my public key can send me a secret that I can get unlocked, right? And how do I do that? Well, this value that I raised to some power, when I receive this package, I take the package, which is some numerical value, and I raise it to another power. What this happens is this is a very, very big number, right? And it is a bigger number than p times q, which means that when I divide it by p times q and take the remainder, I'm going to get back the original number. Why is this? Well, there is a finite number of values that are less than p times q. And there is an infinite number of values I can get by raising m to some power, because I can keep raising m to bigger powers forever, but I cannot find any number more than p times q. So at some point, I am going to loop back and hit the original number again. You don't believe me, but don't worry. I have this many slides to prove it to you, right? So I'm ready. I'm locked in. I'm going to use the term message encryptor and decryptor. I'm not going to refer to m to the power e as the ciphertext very often. That's not a particularly useful way to think of it, but it is in fact a ciphertext. Note that I am saying m to the power e. That is not what we transmit around. We take m to the power e, which is huge. and we take it mod p times q, because we can apply the mod at every single stage of this operation. Modular arithmetic is closed under all of the operations, so it is completely reasonable to raise m to the power e, take that mod p times q, raise the result of that to the power d, take that mod p times q, and get the original number back. And if you don't believe me, talk to Professor Aaron McNicholas, whose students monitored these slides like a hawk and only issued a small number of corrections. Right? There were very few things I said that were objectively false. Do you have a class from Aaron ever?
I have a linear algebra.
Linear algebra, great.
She's great.
Yeah. I love CUDA C++. That's what you did in that class, right?
More, no.
Okay, well, it was worth a shot, right? Did you perhaps multiply two matrices together?
Probably, yeah.
Yeah.
We did do that a little bit.
I do love multiplying matrices by each other. That's pretty much how machine learning works.
We did splines, interpolated splines at one point.
Well, that's cool.
I couldn't tell you what it is now.
It sounds cool.
At the time.
Yeah, it sounds cool, right? I should just teach linear algebra. I keep trying to teach math, and I do seem, in fact, to be quite a bit worse at it than teaching other things. So we're keeping the math to a minimum here. This is the low math version of this class. I don't know if you can tell. I said Fermat for years. It's Fermat, I believe, because I think the French don't say T's or something like that. I don't know. Fermat is in the sort of revolving door of Europeans at a very specific time in history that was like the first European to write something down in a European language and then get credit for it. Seems unlikely to me Fermat was the first person to come up with this, but maybe that's true. I just don't know why I believe that, right? I have a few too many critical thinking skills to assume that every single number theory result was discovered within 60 years in either France or Germany, right? Anyways, Fermat's little theorem is pretty cool and interesting. For all a in the natural numbers and p in the primes. Oh, we're using prime numbers, right? Why are we using prime numbers? Well, we're going to start taking greatest common denominators of things, and any number has a greatest common denominator of 1 with any prime number, unless it's a multiple of that prime, right? So the GCD of the prime and a is 1, which just means a is not some multiple of p, because p is prime. And if that is true, then a to the power p minus 1. So I multiply a by itself p minus 1 times, right? That number gets very, very big, right? And it is equal to 1 mod p. So a to the p minus 1 is probably much bigger than p. I divide it, I take the remainder, that remainder is 1. That is, there is a prime you can raise to a number, you can raise a number 2 in order to get 1 mod that prime. This is provably true. We're doing combinatorics. Combinatorics was by far my favorite subfield of mathematics. I found it dramatically more intuitive than every other form of mathematics. And all of the proofs in my undergraduate combinatorics class were of the form what the professor called counting two ways, where to show that two things are equivalent, you write down expressions, and then you perform transforms to the expressions until you see they are the same. So the forms like, I translate this plain text sentence into combinatorial expressions using things like factorials and so on. I translate this one into combinatorial expressions, and then I apply transforms to them until I see them equal. We're essentially going to do that today. I'm going to use a combinatorial proof, and I'm going to write things down, and I'm just going to say things that are more or less tautologically true several times in a row, and then at the end we will have to conclude that the proof occurred at some point in that series of tautologies, right? We're going to do this by counting necklaces. Counting necklaces was developed by Goulam, who is an electrical engineer at one of the California schools. They're all the same. One of the people that allegedly invented Tetris, there's thousands of such people. I think you can't throw a rock without hitting someone that invented Tetris, as far as I can tell. But anyways, this is one of the people. Do you know who invented Tetris? It was Goulam. That won't be on the midterm, right? Did you take a class from Goulam? He went to a school in California.
I don't think he taught at my school in California. I can't figure out. Do you know his first name?
Is it not linked? Are you not following the slides?
I think not, because he died 4 years before I started undergrad. It would have been difficult.
I assumed this
He
was...
also taught at a private school.
Oh, really?
USC.
That's embarrassing. Imagine teaching at a private school.
It's not exactly UCLA.
It's not exactly, that's true. It is the negation of UCLA.
Or University of Southern Carolina.
So I'm teaching the machine learning class in Salem, and I had to do a sample midterm, and so I had to pick a data set. Have you all heard of ISLR? It's the like legendary statistical learning textbook that everyone uses. Anyways, my impression is the class is following ISLR pretty closely, but not exactly. And so I thought, oh, for the midterm, I will give an example problem from the ISLR, right? This student should be aware of the ISLR, you should have the library installed on your device, right? You should have access to it. I don't know what Hendrik will do, right? Anyways, one of the data sets is this data set called colleges. And it contains things like tuition, graduation rate, percent of professors with a doctorate at colleges, right? And so I thought I would use this as the example for the practice midterm. And basically I found out you should go to public school, which was kind of not a great thing to give a quiz on where the correct answer is you should go to public school at a private school, right? Yeah, Ari, stop nodding. And there's also like, I think this doesn't happen up here, but in Salem, we like get a deal at Willamette where we like can take one class a year for free. So there's like people in like marketing and admissions and like the registrar's office in that class who are all going to get an exam where the correct answer is don't work for private schools. And then I was like, well, I have a bit of an ethical problem here where I can't not use this data set now that I know what it shows, right? Because that would be suppressing scientific results, right? So I'm staring directly into the sun. We'll see what happens. I'm giving the practice midterm on Monday, and we'll see what everyone says. So looking forward to that. I'll report back with the results. Anyways, this is not a paid product placement for PSU. So just remember when we went to PSU and learned about the atomic desktop? Yeah, that was fun, right? Okay, I haven't even applied there. I don't know if they'd hire me. Okay, so a to the p minus 1 equals, a to the p minus 1 is congruent to 1 mod p. This is logically equivalent, not congruent, that is equivalent, right, to this expression, which is a to the p mod p is less than p. No, it's not. We're making this as an assumption. So why are we doing this? If a to the p, well, what are we doing? Right, we need a to be smaller than p. That's fine. We just pick a bigger prime. What's the biggest prime? Does anyone know? That's correct. No one knows. Good job. So there's no evidence we have an upper limit on how big our primes can be. There does seem to be an upper limit on how big of primes we can find before the universe experiences heat death, right? But I've never let that stop me before because I know that death is just a natural part of life. So we're going to assume that A is less than P, and we're allowed to do that because we're allowed to assume arbitrarily large primes until someone writes a proof that there aren't arbitrarily large primes, right? But that proof has been very, very difficult to write. Okay. That slide completely shattered my mental. What time is it? Okay. My blood sugar is getting low, and I've been eating continuously while talking. We'll do a few more slides. Okay. Oh, look, it's another series of equivalent expressions. This is probably what I thought I was presenting on the last slide when I completely befuddled myself. It's important to admit when you've been wrong. Okay, so a to the p minus 1 is congruent to 1 mod p is the same as a to the p is congruent to a mod p. You know what's going on is when I see that expression, my brain is decompiling it into LaTeX. I cannot view that as anything other than equivalent. Do you think these slides would be cooler if I did LaTeX code blocks that weren't rendered and just said like \equiv? Would that be based? I think that would, I think I'm going to change that for next year. I don't like having an external CDN dependency because then I lose bets with Ari, right? So you got to watch out for how much of a good time you have. Is this clear to you? Ask a question if this doesn't immediately make sense. Okay, I'm going to keep going. We're just multiplying by A. This is the counting necklaces thing. Okay, so how are we counting necklaces? I used amethyst and beryl because they start with A and B. The first gemstone I thought of that started with A was agate. I don't know if agates are an actual gemstone or not, so I changed to amethyst. Beryl, I guess, is like kind of like an emerald in some way, right? And then amethysts are like purple. So I'm envisioning purple things. So I have a killer side hustle. I have an Etsy business where I sell necklaces of exactly 5 gemstones, and I select the 5 from the set of amethyst and beryls, and I select with replacement, right? And so when I select 5 gemstones from my set of 2 gemstones with replacement, I can generate a series of different necklaces. And how many necklaces can I do? Well, in the first position I have 2 possibilities, and in the second position I have 2 possibilities, and so on. So I have 2 to the 5th possible necklaces that I can offer at my Etsy shop. So these are the 32 necklaces I offer at my Etsy shop. I think of it as 2 to the 5th, but we can call it 32. And yeah, I have a variety of wares. I like to what do you do with wares? Do you hawk them? I feel like you hawk wares. Does that sound right? Yes. So I like to hawk my wares on Al Gore's internet, and here it is. So I posted this. I embedded this within my slides. I haven't been getting a lot of click-throughs to my Etsy shop, but we do notice that with 5 gemstones and 2 distinct gemstones, I do have exactly 32, and you can write them down here. Did I write that down myself? No, of course I wrote a script that generated this one. So I like to sort the gemstones on my website, right? My Etsy website that I have. And I group them by something called friends. So I have heard that in some cultures, there are humans that have a relationship with another human that they refer to as friendship, right? And these humans often have a lot in common but are not identical, right? And so I grouped necklaces that have a lot in common but were not identical. And the way I determined if they had a lot in common is if they were rotationally related. So I place 5 gemstones facing forward on the necklace, and I have a long chain that goes around the back. But in fact, at any given time, someone can rotate an agate or beryl around the back and place the gemstones in a different ordering, right? So for example, I can have an agate followed by 4 beryls, and that is the same as having 4 beryls followed by an agate in some sense, and so I refer to these as friends. And I wrote this little Python script, and you are welcome. I did not write it as a Lambda expression, even though I wanted to, right? Yeah, right? Yeah. I'll do anything for my fans. And so I can check to see that Ab and Ba are friends. And in fact, they are, because I can just rotate those 2 barrels around to the other side of the necklace. It's 7:30. Go eat dinner. Be friends 5 together. You see why I wanted to end here, right? This is a great slide to end on. Come talk to me if you have questions about any of this stuff.
Yeah, I have a question about when you were converting I guess, the
will say. Azure has absolutely no business working as well as it does. That's crazy. Edge is totally fine, right? It is, it's fine.
Edge for Mac.
It's your fault you have a Mac, Ari. You have to take the fall for that one. But I finally got an AWS for free the other day, so I've used all 3 cloud platforms, and I like Azure a lot. Like, it works way better. And they're not really gaining market share. Google's gaining a little bit, Amazon's losing a little bit, and Alibaba's gaining really fast, and they will continue forever, right? Surely the United States won't have 90% of cloud market share for another 10 years, right? That would be weird. But man, AWS just seems unusable. They like aren't the fastest, they aren't the cheapest, they just have market control, like that's weird. And then the people I know who work for Amazon are like unbelievably good. So they might just be maxed out or something. So there's 2 types of humans. Necklaces. There's necklaces that have friends, and there's necklaces that have no friends, right? If I have necklaces that contain up to 5, or no, precisely 5, of some combination of agates and beryls, each necklace that contains at least 1 of each, an agate and a beryl, is a group of precisely 5 friends. We can think of them as the syndicated sitcom Friends that had 5 main characters. Is this true? One of them is named Ross. There's 6? Okay.
One for each other were friends.
Real?
I think. I don't know, I don't watch the show.
Is there a show that has 5 friends in it? Okay, I can't think of any groups that have 5 things in them. Say we are a pentagram. I don't know, right? So everyone has, okay, so in Friends they each have 5 other friends, right? We did it. You have 5 friends, right? Because there's 6 of you and you don't count yourself. Okay, so perhaps you have 5 friends. I don't know, we're pushing the limits here, right? And those friends are rotationally related. Here's an example of some friends that are rotationally related. Everyone loves it when I pronounce these things. Abba, 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 ba. Those things are all rotationally related, right? And then there's 2 necklaces that have no friends, and they don't remind us of anyone in particular. Okay, and they are and boom. So one of them is a tuba player. Any brass players? Anyone play trumpet? Yeah. What would you play? Trombone? Yeah, let's go. So what am I arguing here? I'm arguing 2 to the 5th, which is the same numerical value as 32, even though we don't like to use decimal in this class, is congruent to 2 mod 5. 2 to the 5th is equivalent to 2 mod 5. A to the p is congruent to A mod p. That's the proof. So, why is this? I don't think it's too hard to imagine. Friends are rotationally related, and if we have 5 joules, we can rotationally rotate exactly 5 times, right? Any one of the 5 in a given arrangement can be the first of the 5, right? So we know that there are 5 repeating instances of any friend group, right? Because after that, if you rotate something 6 times, you've already seen that thing before, right? It's a collision. So the prime, 5, is congruent to 0 mod the prime. We can't rotate more than the number of prime times, and we had our prime was 5. This is true unless there is only one symbol. If there's only one symbol, it doesn't matter how many times we do or don't rotate it. We still only have 5, or p for the prime, of the same gemstone, right? Doesn't matter how many gemstones there are. Doesn't matter how many distinct gemstones we can choose from. We have exactly one case. So we have exactly A strings of this form. Why? What's A? A represents the number of distinct gemstones, for example, agates and beryls. If A were 3, we'd also have corundrums. If D would be diamonds, E would be something else, emeralds. F would be fulgurite. G would be gemstone. Garrett, yeah. H would be something else. So this is a pretty strange example at this point. So you always have a bunch of things that have p friends, the number of primes. And then you always have the number of gemstones things left over. That's what we're showing here. It's the exact same thing, right? Congruence mod p. So that's the counting necklaces proof. If you don't understand it, the way to do it is to substitute 5 for 3 and work through the same example yourself. It is interesting to me because it really feels like a proof that was made on an abacus. That's the first abacus proof I feel like I've done. Feels like you're moving beads around, right? So that's Fermat's little theorem, and now we can do RSA. RSA, I finally learned to remember the 3 names I've been practicing for my entire life. They are Rivest, Shamir, and Adelman. And they probably all worked for the NSA. I don't know. I'm assuming they did, right? Here's what we want. We want m to the e to the d is congruent to m mod pq. We're not that far off. We did congruence mod p, so just 1 prime. Not too big of a deviation, right? We're going to impose some restrictions on p and q. We're promoting them to primes here. We're still not specifying that m has to be less than p times q. You're going to get a message back no matter what m you put in. It's just if pq is too small, you're not going to get back the message you put in, right? We lose precision over time. So we're going to show this. And then we're going to show how to actually use the thing. These slides, beginning a little bit later today, are of the novel form that I have embedded the complete Python solution in these slides, and if you run these slides under Quarto, the RSA algorithm runs when you render them. So we have complete working code base here, and I've provided the example code in a few other places. I've written RSA a large number of times. I do not any longer maintain reference implementations. I just write it from scratch every time. And I think this makes sense because the reference implementations, they might like look unclear to you if you wrote them 5 minutes ago, even though there's nothing complex about them, right? And it's hard to know at any given time what to call the public key exponent or the multiplicative modular inverse or something like that. So we're just going to run through these slides, but don't take these slides as ground truth necessarily. Take them as an example, right? The lab that corresponds to these, which I don't think we have any intention of doing the lab, is just take the Python and translate it into C, and by understanding the Python in C, you will understand it in your mind, and that's fine. A simple translation exercise is more than sufficient to understand this. And if you want to translate it to JavaScript, good luck with your integers, but like I have no problem with you trying to do this in JavaScript, right? It's completely reasonable. I wrote it in C before I ever wrote it in Python. We're going to use something called the Carmichael-Totient function. I just call it the Carmichael function here. It doesn't matter what this thing does. It is essentially a minimal value. And it is the minimal value that, given some n, we find the minimal m value such that m, for all of the values that are co-prime with n and less than n. So I'm counting from 1 to 17. I think 17 is prime, so everything's co-prime with 17. I'm counting to 18. I'm leaving out the multiples of 3 and 2, right? So 5 is still in there. So I need something where I can take a, the value less than m, so it's 5 with respect to 18, raise it to some m power, and get congruence to 1 mod 18. That's the value I need to find. This would be pretty obnoxious to implement and figure out how to solve ourselves, but we're just so happen, completely coincidentally, only ever going to use this on prime numbers. And on prime numbers, it's much easier because of Fermat's little theorem, which is a to the p minus 1 is congruent to 1 mod p, which means lambda value of any prime is p minus 1. This is ludicrously nice because we don't actually have to write code that solves this problem. Instead, we can use minus 1. And subtracting 1 from things is much easier than proving things about them. Right? A lot of what goes on RSA is going to be saying, here's this really hard thing. I sure hope there's a special case that applies to numbers that are 2 primes multiplied together minus 1. And I happen to be holding here in my hand a mysterious number that I created by calculating 2 primes, multiplying them together and subtracting 1. And you're like, that's such a coincidence. That's crazy. I wonder what'll happen next. It'll be like, you might be hoping that your number you're holding in your other hand has the exact properties of Carmichael's totient function. And you're like, oh, that was what I was hoping, right? So anyways, this is a nice feature. What is that going to allow us to do? Essentially, that is going to allow us to encrypt, right? Because if we multiply both sides of that thing by a, well, okay, now we're getting a back when we raise a to some power. Pretty useful. Here is, this is, RSA is a public key crypto system and is not an algorithm. What makes it different than an algorithm? It doesn't describe an implementation. You can implement RSA without using any of the cool mathematical tricks by just trying numbers over and over again until you get one that works. So this is an algorithm, one such algorithm, that describes how to implement the key generation component of the public key crypto system. The public key crypto system is the thing that models the probabilistic machines that are talking to each other and having some transcript, right? So this does not describe what RSA is as a public key crypto system. This is a textual description of key generation, how we generate E, D, and N. And E, D, and N are the things we're going to use to get the ciphertext and then get the original text back from the ciphertext. I'm going to choose 2 big primes. Is prime generation hard? Yes. I think I've maybe told you all of this. The big RSA assignment went out recently. Maybe it's not out yet. Maybe it's going out. Oh, it probably went out today. It is the first assignment I've released in this class before I completed it myself. And I was going to do it this weekend, and then Monster Hunter Wilds came out. But also, like, division really took me a while, so I got behind. And I actually know there's an error in the assignment description that I have to figure out how to correct, which is that you can't do 4096-bit precision RSA with 4096-bit precision integers. You actually need integers twice that big, because you have to be able to multiply integers that big together. So there's one mistake. And then I thought about that for a minute, and I was like, I actually don't know that we can generate primes of size 2,000 digits, which is how big they would need to be ever, right? I don't know how long that's going to take on our computers with the divisions we wrote ourselves, because we're working with unoptimized divisions. I don't have performant characterization for my division. I know I can multiply numbers pretty fast, but I seem quite a bit slower than big GMP. And I know it takes big GMP like a second to generate a big key, right? So if I'm 1,000 times slower than big GMP, I will never know if my code runs or not, because I will give up 5 seconds before it's done. So when I say choose 2 big primes, I mean, let's not talk about what big means. They're larger than 64 bits. And if they were only 64 bits, we wouldn't be able to encrypt very big numbers, and therefore very big messages. But they're also not 100,000 digit primes, because no one has the ability to generate those things. Now, we do know that there's always a bigger prime, because no one's written a proof there isn't yet. But we don't always know what the bigger prime is. So we're going to choose 2 big primes, P and Q, and we will hand wave what big means. Step 2 is my favorite. You multiply 2 numbers together. I know how to do that. I'm completely locked in on that. I noticed that step 2 is much, much easier than step 1, because at least in my prime calculation, what I'm going to be doing is I'm going to be looking at a number and dividing it by every single number that is less than the square root of that number. And every single one of those divisions is going to recursively include a large number of multiplications, because of the way I wrote my big mul. So there's going to be exponentially more multiplications in step 1 than there is in step 2. So step 2 is easy, and that's why I like it. Then I'm going to find Carmichael's totient function of n, which is going to be really easy to find. Then I am going to find the encryptor. The encryptor has a bunch of requirements over it. it has to be less than the totient function, and it has to be co-prime with the totient function. And so we'll talk about how to generate that, and there's a good trick to do that quickly. And then the last thing we're going to do is we're going to find the decryptor. And the decryptor isn't too hard to find. We know there is some value d, such that m to the power e raised to the power d is congruent to m. So we can just keep trying things until we get that number, and we can do the clever thing next week. So those are the steps we are going to proceed through. And I think all of that math looks correct to me. I am recommending, and I wrote it in Python, the simplest, minimally clever way to generate primes that I'm aware of is 6k plus 1. Why do we do 6k plus 1? Well, most numbers that aren't prime are not prime because they're divisible by either 2 or 3. Which means that we can just look at things that are of form 6 to the k plus 1 and are necessarily not divisible by 2, and are necessarily not divisible by 3, and are necessarily 6 away from the next number for which that is true. So we try 1/6 of the numbers. Naive witness checking is 6 times slower than this, and the most advanced algorithms are much faster and looked hard to implement. Most large-scale prime generation generates these things called probable primes, which are probably prime. Those don't work because they're only probably prime. So you have to actually make sure they're prime. There are efficient ways to make sure things are probably prime, and they are barely faster than just doing this, right? So you might as well not learn a bunch of number theory. You're already taking a class on number theory by accident, so you're in over your head. I looked up the algorithms. I think there's something called like the, I guess I didn't put it on this one, Pollock, someone algorithm that's incrementally faster than trying every number. Looked absolutely miserable to implement. I didn't bother. I'm assuming GMP next prime does that. If my code base explodes, I will use GMP prime generation and then run the rest of the code on my 496T library, and that's my backup plan, because I want to make sure that I can get this to work well. So here's prime generation. This is quite fast in Python for any reasonably sized number, and then everything is slow for large numbers, so it doesn't matter that Python's 50 times slower, because that only slows you down by 2 digits. N was my favorite thing to calculate. N is p times q. So I'm going to find large primes. I'm going to throw a k value in here. You will notice that this is not probabilistic. I don't have any built-in random generation at this time. I am just going to put a number k in there, and I'm going to get the next prime that is bigger than 6k plus 1. So I am providing the randomization by typing into my computer, and I am truly random. N is p times q. That was my favorite step. Now, we're going to compute lambda of n, Carmichael's totient function of n. N is p times q, p and q are primes. This is super duper mega secret, right? And why is this super duper mega secret? Because if someone knows this value, they can pretty quickly figure out your private key. And no one is allowed to figure out your private key, because if they figure out your private key too fast, Edward Snowden has to go to jail, and we don't get to see him appear on Fox News, right? Do any of you watch television?
Fox News.
Do you watch non-Fox News television?
I don't watch live TV.
Okay, right. I'm trying to find the oldest person that doesn't watch TV and the youngest person that does watch TV. Because I think they were born like 8 seconds apart, and there's just like a firm line somewhere temporally, right? And I don't know if it's age-based or like mood-based. So my impression of students is, even though you're not all the same age, you're like one gestalt consciousness that shares all of the exact same lived experiences. I don't know if you've noticed this about yourselves. You don't have any individuality until you graduate, right? So that means that if there were somehow like a 76-year-old in my class, that 76-year-old would not know how to watch live television, is my theory.
I mean, have you met 76-year-olds recently? TVs have gotten complex enough that they no longer know how to watch live television anymore without intervention.
So what you're saying is that my analysis is correct.
Yeah.
That's what I thought. Okay. There is a fast way to do this. It so happens that lambda of PQ for primes is equal to the least common denominator of p minus 1, q minus 1. I'm going to leave this as an exercise to you. I told you what Carmichael's totient function is. It's just do some multiplications. Like, that's all there is to it. Don't worry about this too much. You will know this works when you successfully encrypt something, then decrypt it by raising it to a power. I love GitHub Copilot, Microsoft. We were talking about how much we love Microsoft. I love GitHub Copilot because I forgot what GCD stood for. So I just asked it, and it gave me this code, and this code was easier to read than greatest common divisor. I was sure it was denominator. Do we think Microsoft is wrong? We learned through the same thing. Did you stream long division on mega.nz? I noticed there were not very many listens to that song, even though I worked very hard on writing the lyrics for it. Should we listen to it now? I probably have it in Discord. Mega.nz. Oh, it's a video, I forgot. Oh, I'm muted. Never mind, this won't work. Okay. Anyways, I made you all a song to the tune of Bad Decisions by Bad Omens, and I say long division instead of bad decisions. And I feel like only slightly hurt that no one interacted with the post in Discord after I made a song for you all.
I treat links that you send in Discord a little bit like a QR code in a public place, where it's like, if I'm going to visit them, I'm going to like...
Sandbox, yeah. That's why I taught you about Podman. You can just run your Flatpak in there, right? Okay, so the greatest common divisor. Does that code make sense to you? Doesn't make sense to me either. Okay. You know how to find the largest number that divides two numbers, right? You try things. Write a for loop, right? If you want to be clever, do that. That is actually the Euclidean algorithm that we're learning next week, so we don't have to go over it now. We'll come back to it. But you can get this to work, and you can just use that sample code. So E, do you remember seeing that scary mathematical expression? Oh, I need an E that's like not as big as lambda of m, and also that the GCD of E and lambda of n is equal to 1. There's this fun little trick where prime numbers are co-prime with other numbers because they just have to not share a common divisor. And prime numbers don't share common divisors with anyone. So we just use a prime number. And we always use 65537. Why is that? Some of you, perhaps all of you, wrote big multiply. And you might have noticed that it was slightly harder than pressing the asterisk key on your keyboard, right? I don't know how much harder, right? While you were doing that, I hope you were thinking, those poor electrical engineers that are responsible for making CPUs, they had to implement their own multiplication. And I don't actually know how you would necessarily do that, right? So perhaps it's not too bad to imagine how you would take the sum of these values, right? So if you just had transistors, if you had 8 transistors in your left hand and 8 transistors in your right hand, and the first 4 transistors in your right hand contained electrons, and the first 2 of each of the sets of 4 transistors in your left hand both contain 2 electrons. I think you can imagine, if you're an electrical engineer, you can attach wires to these such that they check to see where the electrons are and perform an addition operation. And it is perhaps not the hardest thing in the world to imagine what that addition operation will do, which is importantly have a carry bit, right? Well, you have no low order zeros, so those stay 0, and you have a series of 1s. And then when you add these 2 1s to those 2 1s, they just all roll over, right? So that's not too hard to implement in terms of bits. Do you have any idea at all how to do this? Like, that doesn't look easy to me, right? I think that I could teach an elementary school student to do that in like 3 months or something. Or like it would take a long time. You'd have to be like taking notes, you'd have to be using documentation, right? Alan Turing, when talked about the Turing machine, said like the notion of computation is like if you give extremely exact instructions, a human could do it, right? What are the extremely exact instructions that you give to a second grader to perform binary multiplication? I can't even imagine them, right? But the first thing I would do is teach that second grader about bit shifts. Because here's a way to make this a lot easier. If we just have these values, if we only have 2 ones, it's not too hard to think about this. Because if I multiply this by 1, well, let's look at them. If I multiply this by 1, I get the same value back. If I multiply it by 1, 0, I add a trailing 0 in binary. This operation is the same as a single bit shift, which means that if I can teach my second grader what a for loop and a bit shift is, I can implement multiplication with a combination of for loops and bit shifts. I loop over every single bit, and if that bit is present, I shift by that much, and then I perform an addition. So you can implement multiplication, and I did not do this on Big Mole. Now I'm wondering if I should have, right? Should I have written that you do a bunch of bit shifts and add? I don't know. I think on big multiplication it was too memory inefficient to justify doing that, but I'm half inclined to go back and write the bit shift version and see if it's a gazillion times faster, because it might be. Because you only have to keep track of one running sum, and you just have to keep performing bit shifts and adding to it. That's probably really fast, right? So I found, what is this thing? Oh, that's actually very funny that it's all ones and zeros. But we can say, oh, this one's better, perhaps? No. Here's the first thing I put in. But I can say, I can take this first value, and I can shift it over by, ooh, I'm going to just save this in a variable. I'm going to say x equals b110, okay? Then I'm going to do bin, I'm going to do x, shift it over by 1, 2. Is that a shift of 2? I think it is. 2 plus 3 plus, is it 6 and 7? Nope, that's wrong. Oh, I probably need these things? There we go, that's correct, right? Exact same value. I can decompose my multiplications into bit shifts. This is very cool, and it is very good. Because I might have to multiply things a lot of times, right? 65537 happens to be prime. It's a prime of some form. There's Mersenne primes and Fermat primes, and I don't remember which one's which. I would assume this is a Fermat prime because the name of the lecture today is Fermat, but that might be incorrect. That is 6 to the power k, or no, it is 2 to the power k plus 1, which means that I can multiply by this number with 2 bit shifts, which is comically easy to do. That is a bazillion times easier than multiplying, right? So I don't have a sense for how you would have a chance at all of implementing multiplication in digital circuitry. I'm not like a digital logic person, right? But you can get it to work with bit shifts, right? And that insight is pretty important. And that insight is pretty important because I was able to get long division working once I had multiplication, right? which means that once I had this insight, I can actually design a circuit that can do division, right? And I couldn't do that until I realized this bit shift trick. Because you really can't afford to do repeated addition, right? That's not having a computer, right? So that's why we use 65537, the encryptor. This is called Hamming weight, Hamming, presumably someone's name, I don't know for sure. And incidentally, this number has the lowest Hamming weight of any prime that is not 2. 2 is the only Hamming weight of 1. It has a single 1 bit in its binary representation. All other primes have at least 2. Here's an example of a prime that is much smaller than that has a much higher Hamming weight. 7. 7 is prime. 7 has a 1 in the 1's place, a 1 in the 2's place, and a 1 in the 4's place in binary. So its Hamming weight is 50% larger, even though it's a much smaller number. Which means that if I were to multiply something by 7, I would have to perform 3 bit shifts, which means it is harder to multiply by 7 than it is to multiply by 65537.
Do you think that every other prime has more than 1?
At least as many. Why do I know that? They're all odd, so they necessarily have a 1. And then they necessarily have one other value because they're all larger than 1. So the minimum you can have is 2. Now, 2 is prime. Many mathematical proofs, I think, say 4 primes other than 2, because 2 is a little bit too special and too weird, right? But 2 is the prime that has a Hamming weight of 1. So there is one thing that has a lower Hamming weight. That's it. It's just that one. And then there are 5 known, I'm going to call them Fermat primes, I don't know if that's true, and 65537 is the largest one, to the 16 plus 1. Should we check if they're Fermat primes? I feel like we should make sure. Oh, it's even more specific. Oh, Fermat number? Oh, Fermat primes, okay. There are only 5 known such primes, right? And they're all great fun. So we love our prime numbers, don't we, folks? Okay. I have claimed that no one knows what the biggest prime number is. That is true. Also, no one knows what the biggest Fermat prime is. But it is weird that we know primes of several thousand digits, and their largest known Fermat prime has 5 digits. So there's no real reason to believe that there's a bigger one of these than 65537, and certainly no one's found one yet. And they're looking because it's the basis of the most successful and powerful crypto system in human history, right? So people checked, right? They spent a lot of money on this. They could find none. People much, much smarter than any of us worked on this their entire life and could find none. This is my motivation series of questions to get you to consider the things we just stepped through. The last thing to find is D, the decryptor. The decryptor, and I'm only going to say this out loud, is the multiplicative modular inverse. Mod something, right? The MMI, I often call it. And what do I mean by multiplicative inverse, or modular multiplicative inverse? I think you usually say modular before multiplicative. In my mind, it's just MMI. I don't know the order. The multiplicative inverse of something is the value that you can multiply that value by to get 1. The multiplicative inverse in the natural numbers doesn't exist. Because when I take 2, I can multiply something by 2 to get 1, which is the multiplicative identity. But that thing that I multiply it by is 1/2, which is not a natural number. In the real numbers, I do have 1/2. So I can multiply 2 times 1/2 and get 1 back. I can multiply 3 times 1/3 and get 1 back. We are working with the integers, which would suggest to me that there's no way to get multiplicative inverses, right? It seems like that's impossible. No matter what 2 integers I multiply together, I get a bigger number. But I am working in a modular number system, which when numbers get big enough, they loop back around to 0 and 1. So I am finding the number that when I multiply e, which is 65537, times some value, the remainder of that, with respect to the Carmichael's totient function, lambda, which is the LCM of P1 minus 1Q minus 1, and don't worry too much about all of those things. You'll have these saved as variables in your script. You can just look at them, you can read the comments and see what they do. I have some value that I'm working modulo with respect to. I have some e value, 65537, and I just need to find some d that when I multiply e times that d, I get 1. Now, you can definitely guess and check this, and why can you do that, right? Well, whatever that number is, it's going to be less than lambda then, and lambda then is only going to be so large, right? So you can do a finite number of guesses, and you can find this. So you can start at d equals 1 and go up until you find the value. You don't actually have to check d equals 1. You know it's not that. You can start at 2. And you can be a little more creative than this, but fundamentally it doesn't cost that much money to check everything, and there's an efficient algorithm we're going to learn next week. So it's not too bad.
So D is unique. Is that the idea here?
I don't think it matters that it's unique. I would assume that it's not. I think you just want the smallest one. Yeah, I would assume there's infinite satisfying Ds.
Yeah, because it doesn't matter how you decrypt it as long as you decrypt it.
Yeah. I think of this in terms of collisions, right? So when I raise m to a certain power, there are an infinite number of values that are equivalent to m to raise to that power, and there's a finite number of values modulo lambda n. So there should be an infinite number of Ds, I think. I suspect there's an infinite number of multiplicative modular inverses. I would not know how to write that proof, but that's what I suspect. That's RSA. We're going to step through the code example, and then I'm going to ask you what you want to do, which is either you will work on this while we'll talk to you, or we'll find something to show you. The thing I would most likely show you is we'd screw around with modular arithmetic a little bit, and then the other thing we can do is talk about how large of values we can store. There was a very good question in the Discord where some students said, wow, I can encrypt values of exactly 4 bytes and not at all bigger. That's so weird. I wonder why. And I was like, you really should be able to figure that one out yourself if you think about it. But like, it is academically interesting to explore why that is. So that's something we can cover. Okay, so we're going to use RSA. I'm going to use Python. Why am I using Python? Very, very simple. The entry-level categorization for numbers in Python is integers, and the integers are arbitrarily large. So the two things that can make RSA hard, which is not having integers and not having big enough integers, both do not happen in Python. So Python is well suited to education in RSA. It was ludicrously bad at SHA. Remember, we couldn't get it to do anything because we couldn't get to bits in Python. We're not dealing with bits anymore. We're only dealing with numbers now. We're using bits to store the numbers, right? But it's actually quite nice to do RSA in Python. And you would never use Python and RSA for practice because Python is slow. We're just going to make a random string. I just arbitrarily selected a letter. I don't have any personal feelings towards this letter. It's not like a favorite letter of mine. So this was actually chosen by a random number generator, me. Oh, it's C. Okay. I think for you all, I pretend to like Python a lot. For the undergrads, I pretend to hate Python. So I just go back and forth. I don't have any true opinions, right? I wrote my prime tester. You remember in 6k plus 1, I just said you check if this number is prime, and if it's not, you add 6. It's very easy to check to see if a number is prime. I did it in a single line here. That's a range generator. I guess I will say what this code does. Given some number n, I take all numbers in between 2 and the square root of n. Do I actually take the square root of n? No, because that might not be an integer, right? So I take the integer form of the square root of n. Now, I don't know what int does in Python, and I don't think it matters. It either takes the floor or the ceiling, probably. Maybe it rounds. That doesn't affect me, right? Because the thing that is smaller than the square root doesn't matter. And the thing that is bigger than the square root doesn't matter, right? Why can I do this? So if there's any two numbers which multiplied together produce n, one of them is less than the square root, right? So I take each such number, and I take n modulo that value. What's this doing? This is checking to see if I evenly divides n. If I evenly divides n, it may be a factor. If I is a factor of n, then n has factors, and if n has factors, n is not prime. This is witness checking. I'm checking to see if there is a witness that this number is not prime. So that's my prime checker. I just threw in a Python any there. I don't know if you all use any anytime. I see some pretty esoteric code written by students that claim they like Python and they don't use any at all, and I hate it, so I just incorporate a bunch of any's into class. And every single student in Salem undergraduate hates the fact that I use lambdas, so I dogmatically refuse to use anything else. We can check to see if 60 and 61 are prime, and of course 60 is not prime because it is divisible by 3, and 61 is prime because it is divisible by 1 and 61, and nothing else. And we don't check 1 or 61 because 1 is less than 2 and 61 is more than the square root of 61. I can generate 2 primes quickly. I am adopting the convention of hiding numerical values that you should not store in plain text on your physical device. And I am hiding them inside functions because I am a functional programmer and that is the correct way to hide things. Are these in fact very easy to get to in Python? Yes, of course, we're not actually doing security, but I am showing you the convention and in fact the best practice that you should not have P and Q floating around on your system somewhere. And so I have hidden them in something called hide P, and in fact, if you evaluate hide P at the command line, it says function at this location, and it does not give you the actual value. It is relatively hard, even if you gain control of someone's system remotely, to start reading things out of memory, and it is dramatically harder if you have to call a function or see a return value written within some function closure. So that this would make things harder on an attacker, but not hard enough. You should do better than this. And the way to do better than this is to throw SHA at everything, somehow SHA everything. So here we have 2 primes, and they have a product. If you've been following along and running this own code on your own device, you can figure out what P and Q are, right? I'm not revealing them on the slides to demonstrate you don't need to know that. So this is n, we generate our 2 primes. I didn't know what to call lambda, so I called it lambda to avoid confusion with the other lambda, right? This is quite nice because there's 2 ways to express lambda. You can both use the character and you can write out lambda, so these things look completely different. So I wrote a lambda expression called hide lambda, and it takes the LCM of hide P, which is P, and hide Q, which is Q, subtracts 1 from both of them and computes the LCM. I didn't write that LCM function myself. Google plagiarized it from LeetCode. It's very obviously from LeetCode if you've ever seen any LeetCode. So anyways, and I am not revealing this. Why am I not revealing this? It would be a little bit too easy to figure out P and Q, and therefore my decryptor, which is my private key, and then figure out the identity of Edward Snowden, if I did not keep this at least a little bit secret, right? So while the FBI is figuring out how to evaluate functions in Python, Edward Snowden will be squirreling away on a plane to Moscow, where he will live a lavish and critical of the United States existence, as we all aspire to do, right? The public key is public, it is unsecret, and it is 65537, the same as everyone else's, right? We love our public keys, just like we love our public schools, don't we, folks? There's a callback, all right. I did apply for jobs at public schools, and turns out, I didn't know this. It turns out I had decided that I wanted to live in Portland, Oregon. I didn't know this when I was applying for jobs. And there are no public schools here. PSU does not count. I don't know why it doesn't count. Have any of you looked at programs at PSU? They have an MSCS. It's not in evenings though or something, right? Yeah. There's nice people there. I know quite a few of them. Okay, so this is how I find D, the decryptor. We keep the decryptor secret, so I have it hidden away inside a function, right? I start with 1. I shouldn't probably have started with 1. And what I do with my candidate decryptor is I multiply it times the encryptor, the encryptor. The encryptor and I take that value, that product, I compute the remainder of that product with respect to lambda, right? And I see if that thing is 1. If d times e is congruent to 1 modulo lambda of n is what that is, then I have found the multiplicative inverse of e with respect to the modular base lambda of n. And that is useful. Why? Because what can I do with this one? This one tells me that I've raised to something to the same power that loops back to be equal to itself. Right? I want that 1 because that 1 is the identity. As long as it's not 1, I just add 1 to it. Or as long as the remainder of the product is not 1, I just keep adding 1. Right. This is a little bit slow on bigger values, and it's fast enough for now. And the fast version of it is confusing enough to merit another lecture. So we're just doing guess and check. I love Python. I do. Because Python, as I said, allows you to use arbitrarily large numbers. And by default, it has integers. So I did a very, very simple operation, right? I took my string, which was the randomly selected string. I think it was C, maybe something like that, which was the grade I got in my undergraduate complexity theory class. Still got into grad school, right? Good for us. I convert that to an ORD. It is the ASCII or UTF-8 numerical value that corresponds to a character. All of the individual characters are 64, or what, no, they're 256 or less, and we can see other things, right? So lambda is not an ASCII character. It is not a UTF-8 character. It's a Unicode character. It is a Unicode extension. So it requires more bits. You probably don't believe me. It's a larger value, right? Not that much larger, right? But so that's going to be UTF-16 or probably UTF-32. Not really super into text encoding, so I don't know too much about it. But I do think it's funny. You can just slam like the character lambda into Python, and that's not a special character, but if you type out lambda, it's a control flow statement. I don't know, I think that's mad goofy, right? Like, I found out, did I do this with you all? Did you know assert is a control flow statement? I thought it was a function. I had no idea you could do this.
Sounds like something they should change in Python 4, like they did with print in Python 3.
Right, like why is that against the law? Right, I think people print more than they assert. That's what I think, right? But I guess you could be like, oh, like test the truthiness. Right?
Testers are too assertive.
Yeah. What happens if? Can I put an assert inside a lambda?
I think assert is both. Is it not both a control flow statement and a function?
It's probably both, because print used to be both. I'm going to see if this is basically an even checker, right? Okay, that's not allowed. Is this allowed? This is why we did monkey type. Ah! Where are my hands on the keyboard?
You may not be able to.
It looks like this is banned. Okay. Oh, no, I need an argument.
Well, you can put it in a function.
Can I?
Yeah. Otherwise, you'd never be able to check your function. Check your arguments using
Can
assert.
you use the assert in front of lambda?
We'll try. Okay. And so we're going to try and assert a lambda. Yeah, that's fine. Because it's truthy. Functions
Yeah,
are
I'm just
pretty
thinking
good.
of things to try and do a thing equals lambda x assert, and just move the assert to be in front of lambda. Does that end up working out?
Yeah. It is pretty weird you can assert lambda none. It doesn't seem like you should be allowed to do that, but then there's like no intuitive reason why it wouldn't work, right? Because it's not like lambda none is false, but it does in fact return none, which is falsy. Because I don't know, that's pretty odd to me, but what do I know, right? But really, of course, what we should do is f should be lambda none. I don't know, okay. Hold on. Are we having fun? Yeah, okay, so that's recursively defined, and then what am I doing? I've lost my mind. Sorry. Anyways, I nerd sniped myself there. You can add functions to themselves as an attribute. Why can you do that? Write C. Okay. Python lets you do that because Python lets you put pointers to things everywhere. This seems bad and wrong to me, right? It seems like if you take a function and you say like, hey, I want this function to have an attribute that stores some value, that should cost money. Like you should get charged for that. You should get a segmentation fault if there's not already that field named. But there's just all kinds of things in Python that you can do that like don't make sense. I guess you can't do that to print. That's nice. Oh, I bet I can do like I don't know. That just seems like it shouldn't be allowed. Anyways, here's the decryptor. I didn't write this as a lambda. My gift to you, right? I could have done that. Okay. So Python, known terrible language, absolute train wreck, right? Hate this thing. You can also see where my Python installation is, which it's in app data. Well, I guess I ran this on Windows, right? So that's in app data local programs, right? And separately, you can also see that I was running this as an interactive Python notebook, a .ipynb file. Why is that? Because when I hit Quarto render on my computer, for some reason, the people I'm going to refer to affectionately as the brain geniuses at Posit decided that the most reasonable way to run Python code embedded in a Quarto markdown document is to rip the Quarto markdown document to a JSON interactive Python notebook file and run it through the Jupyter Notebook kernel.
So far.
So, hear me out, right? There is such thing. Oh, I don't have it. Do you all know what line magics are? Line magics are cool. Oh, I'm not going to have Jupyter. Well, maybe I will.
Oh, yes.
I think
You
it's...
can like pip install something from a Python cell.
Yes. I don't actually know that my computer works, so we're going to open our most beloved web-based cloud service, Google Colab, named after one of our top 3 favorite trillion-dollar companies that isn't NVIDIA, right? Because obviously NVIDIA is number 1 in all of our hearts, right? I was teaching some graph theory the other night. That was fun. Why did I do that? I want a new notebook. I'm conducting academic research, learning Python, using teaching or leading a classroom. I'm working on personal projects. Okay. I am a professor. Okay, cool. So there's a lot of ways to run Python code. This is one such example. How do I delete this cell? There it is. How much stuff was there in here? I don't care about any of that. And that's one valid way to run code, right? But would it not be way cooler to, does this work? Python script magic. How do I use bash? Does that work? Flying magic ls exists. Okay. So, is there like a... Dang it.
They have specific defined line magic functions. Oh.
So wouldn't it be like way cooler, right, if you're super into scientific computing, to have a notebook format that only accepts bash? Or sorry, I think we have a Z shell user in here that accepts cell scripting, right? How much cooler would that be? And then I was like, I can probably write that. So I think maybe I will do that this summer. But what I really want is I want my markdown files, when I write them to have code blocks that open a podman container, execute the script inside the podman container, and then dump the output into the markdown as like code formatted or something. I don't know. It's an academically interesting exercise to think about. So Python cannot actually raise numbers to powers. The numbers are too big. Think about this really quick. I think I demonstrated that S was 67, perhaps. How many digits do you expect that to have? It's a 5-digit decimal number and a 2-digit decimal number. If it were 100 to 10,000 or 100,000, I think we have some sense of how big that would be, right? I might be able to store this in a variable. That's fine. It's printing it is not allowed, right?
It's going to be like 15,000 digits.
Something like that, yeah. This will tell us, right? Divide that by 3. What'd you say, 50,000?
13,000.
13,000?
Because if you're squaring a 2-digit number, then you will get a 4-digit number probably. If you're 65537ing it, you'll probably get 2 times that number of digits.
Yes, if I'm 65537ing it.
My favorite operation.
Well, it's easy. You just imagine there's a rectangular prism where all sides are the same length, and it's in dimension 65537, right? Then it's trivial, right?
Yeah.
It just follows, right? It's the hypervolume of such a solid. So anyways, this absolutely cooked interactive Python notebooks. You can get through this with Python utilities and .py files, but I do not have the ability to embed those in my slideshows yet because I haven't implemented my own code base. I'm just using posits. Anyone love RStudio? Yeah, can I hear it for RStudio? Okay.
It's the greatest Electron app.
It feels like a website.
You
like.
can open the console by accident really easily.
Okay, I've never used it.
You can just inspect elements since they don't have any context menus implemented.
Interesting. Okay, we're not gonna fiddle around with our favorite web browser, VS Code, right now. Okay, so how do we solve this problem? Easy. we are doing everything with respect to some modular base. That modular base is lambda of n. Lambda of n is equal to the LCM of p minus 1, q minus 1. P and q are primes. These are primes that we used in our key generation, right? So, because we're doing everything with respect to some modulo value, we can apply that modulo value at each stage of exponentiation. What does stage of exponentiation mean? Well, we can perform exponentiation with this little trick called repeated squaring. Every time we square a value, we can reduce what power we raise that square to by half. Let's look at an example, and we'll see if I can get this right, because I very rarely do get it right due to not knowing precedence. So we have 10 to the 6th, which is a 10 followed by 6 zeros. We can compute that value in another way, which is that we can take 6 and we can divide it by 2, and we can raise 10 to that value. But we don't actually want to raise 10 to that value. We want to raise 10 squared to that value. Let's see if this is correct. Ah! I need to do more monkey type. Okay. So when we square a value that we intend to raise to some value e, we now only have to raise it to e over 2. Remember, we are raising this to the encryptor value, and remember that encryptor value is very, very close to being exactly divisible by 2. So that is really, really nice. We're just going to multiply the whole thing by whatever m is once, and then we're just going to do this sort of repeated squaring all the way down. This works well for any number. Oh, I can only do it for even numbers, right? So let's see, this is y, and this is y. I think it works for 8. And it'll work for, what's someone's favorite even number? It's 56, I know, you don't have to say it. Oh, look, no, it satisfies the equality. Right.
If you use 2, is it conflict with anything? Because it's also a prime?
No, it's just that it's even. The reason the odds don't work is actually due to a rounding error.
Oh.
Yeah. This thing breaks. And the reason I put an integer division there is I wanted to be getting integers back.
Mm-hmm.
That is this line. That is the even case. We take m to the power e. I use e here by convention to refer to the encryptor. You could use this exact same thing to raise things to the power of the decryptor, right? And I use n for the modular base. So that is the message, the encryptor, and the modular base. That's why I used MEN. If e is 0, that means we're raising m to the power 0, which is 1. If e is equal to 1, we are taking m, but m could potentially be bigger than n. Could it really? No, but we take mod n as a precautionary measure. Then we check to see if it is odd, and we will come back to this. So in the even case, we square m, we apply the modulo. Why do we do that? Say m is a 16-bit number. How big is m squared? It is a 32-bit number. The size of a product in bits is equal to the sum of the sizes of the factors in bits. M has 16 bits. We square it. It has 2 times 16 bits its square does, which is 32 bits. Here's the problem. If we raise a number to power 65537, we are going to add bits a bunch of times, right? We're going to add digits a bunch of times. So rather than having numbers grow arbitrarily large, we know we're never going to need a number bigger than n. So we take it modulo n at every stage of the exponentiation process. This is really, really useful to you if you just implemented a 4096-bit library, because all you have to do is make sure that m times m is never bigger than 4096 bits. Otherwise, you would have to use an infinite precision library, and that would use potentially infinite memory. And I don't have a hot startup coming out of Silicon Valley that is selling infinite memories yet. I was talking to a student today, this is a vaguely related anecdote, who was trying to simulate a quantum computer. And this student had not quite gotten totally locked in on what happens when you try and simulate quantum computers and how much exponential stuff you have going on. So one of the conversations we had is, well, I don't need that much information to store 3 quantum bits. You actually need quite a lot, right? And the reason for that is quantum bits can be in ambiguous states. So those 3 bits can be in any combination of states, which means you can have essentially 8 different possible values, right? In a quantum computer, you don't store the value of the output of a function, so you don't store a value 1 through 7, right? You don't store one of those. Rather, a quantum computer tells you every possible outcome. And the number of possible outcomes, if we are storing things in 3 bits, that's 8 possible outcomes. So we need to see if any one of those 8 possible outcomes can be true. That is the same as a bit string of length 8, which means there are 256 possible values that can be stored in 3 quantum bits. That's how bad exponentials are, right? 2 to the 2 to something. We're using a Fermat prime, which is 2 to the 2 to something plus 1, right? So we are dealing with things that get that big, that fast. Human brains cannot process exponents, in my view. Maybe there are people with special training or non-standard intellects or special backgrounds that can do this. There is no way you have any intuitive sense for what raising something to a 5-digit number is. Like, we can't process that. Those numbers don't exist, right? They don't exist in the universe, right? I remember I was talking to, something I perceive as a large number is Avogadro's number, which is like the number of molecules in a gram or something, right? And it's like 6.2 times 10 to the 23rd or something, right? This is like a comically huge number. Like, this is very close to the number of atoms in my body or something, right? And I have to square that several hundred times to get 2 to the 650. Like, they're not even close. These are not the same types of numbers, right? It only makes sense to think about this number in terms of how many bits it would take to store it or something like that, right? We don't want to deal with numbers that big, right? So we take the modular. There is the one special case. The special case occurs 50% of the time, and it is when E is odd. If E is odd, you cannot evenly divide it. That's no problem. We just additionally multiply by 10. And that's simple. We take the first time we multiply by 10 sort of out front or out behind. 10 to the 7th is equal to 10 times 10 to the 6th. Easy. We've already computed how to calculate 10 times 10 to the 6th. So that's all. We just pull out m, and we multiply m by the rest of the exponential operation. So this is recursive mod exp. I think mod exp is the common term for this. I don't know how true that is. Modular exponentiation. It is sort of one of these fun, I don't know, derived mathematical expressions. It takes 3 operands, which is sort of an unusual number of operands for a mathematical expression to take. It's 3 to 1. And it's really fast. So if I do this with 65537, how many times does it run? 2 to the 16th can be divided by 2 16 times, so this loops 16 times. Very fast. Relatively small number of calculations, right? When I looked at this, I was like, oh, like, isn't multiplication really expensive? But no, this is, at the price of 16 multiplications, I do arbitrarily large exponentiation, right? This to me is unheard of. This is the same level of insight as the bit shift, because once I saw this, I knew how to do exponentiation with bit shifts, right? Because this is just a bunch of bit shifts over and over again. This is just not that hard to do, right? You can do this by hand if necessary, right? And it's much easier with a modular base because you get to work with much smaller numbers. So this works quite well in Python. We note that the ciphertext is considerably larger than the message. Why is that? The ciphertext is bounded above by n, so it is going to be some number less than 65537, and in fact it is. But 65537 is much bigger than 67, so it is not unexpected that however big our ciphertext is, it shows up as a larger number. We have our find d value, which is computed by finding the multiplicative modular inverse. We take the cipher value. I took it mod n. I don't have to do that, right? N could be any given value, right? And so I take the cipher value, mod n. I raise it to the power of d, also mod n. And then I see the new message and the old message, and they are the exact same value. They are our most beloved language, C89, right? It's a little sad that the ASCII code for C isn't 89, but I can't actually change the international standard just to make a funny quip in class, even though I tried. I sent IEEE an email. And I encrypted it using public key cryptography so it looks suspicious. Is it good? C, yes it is. So, what is this? That is modular exponentiation applied twice, the first time we encrypt, the second time we decrypt. And then we just convert in between characters and numbers. So that's what the OR and char are doing. And so that's end-to-end RSA public key encryption. This is the whole code, end to end. Not too much. I'm still not embedding this stuff with Calvinism that Ari made for us because I can't get the colors to match. It's a weird thing to be annoyed about.
Speaking of Calvinism, if you really want to make that fun, you should write your own C compiler just for that.
I should.
You can call it Calvin CCC or?
Yeah, I'd call it CCC, yeah.
Oh, you already, okay, you're one step ahead.
Yeah. It also stands for the Civilian Conservation Corps.
Well, now it'll stand for the Calvin.
The Calvin C compiler, yeah.
Isn't Calvinism wordy religion?
Yeah, it's like a sub-religion, right? It's the predestination Christians, and they're loosely related, I think, to the Pentecostals now. Pretty interesting philosophically. I don't know if you want to talk about Calvinism, right? But they have this interesting notion of predestination, where it's like many of the other, my inclination was to call them Christian sects, S-E-C-T-S, which could be perceived as offensive. So I think I'll say denominations, but they could also just be schools of thought or something, philosophies, right? Is like, oh, a common claim is that like some permutation of you, if you accept Jesus as your Lord and Savior, you will be saved and go to heaven when you die, right? And the Calvinist position is that like who goes to heaven when they die is predetermined by God or perhaps by some naturalistic process, right? And so that like, oh, can you accept Jesus as your Lord and Savior? And what they maintain, and I thought this was interesting, and I have not seen many people actually respond to Calvinism this way, which is like, it was always presented to me when I was raised in a Lutheran sect, like, oh, that's weird because they don't believe that like if you accept Jesus as your Lord and Savior, then you're saved. But the Calvinist position is not actually that you don't do that. It's that just God already knows if you will do that or not. So you still go to heaven the same way. The position is just that it's politically or culturally relevant that God knows the future, right? Which is such an interesting permutation. It's like there's only predestination because that's an application of your understanding of divine omnipotence or omniscience, right? Which I thought that was really interesting. So it's like, if I already know that something's going to happen, do I still make decisions? And of course, I don't care, right? But probably this matters a lot to the philosophers. And this is much more relevant, I think, to the quantum computing thing, right? So there's like some number of humans, and some of them are going to accept Jesus Christ as their Lord and Savior, right? But it's actually 2 to the number of humans, different quantum possibilities, right? If you're trying to figure out which religion is the correct one, which is an enormous number. And this is probably why none of the proofs of the existence of God go through that well, right? So I find Gödel's ontological proof quite convincing. But it doesn't say anything about how you go to heaven, right? Which is the real relevant bit for me. Like, I'm not personally directly impacted by the existence of non-existence or God, but if there's like an afterlife, I want to go to the one that has Monster Hunter Wilds in it, right? Okay. My recommendation is you should ask me questions that you have, or you should get this working and see while I'm here to help you. The organizing framework to get this working in C, well, I'm here to help you. I can, in fact, start the Euclid lecture, and we will get absolutely nowhere in 38 minutes. It would be like I will leave you worse than I started you. So my recommendation is to look at keygen. The planned enrichment lecture for this, I just need to I have the notes for it, and I haven't figured out how to present it yet. I wanted to step you through the process of how I generate and save and examine, I think I'll say, public and private keys that I generate with existing command line utilities on my device. I think it would be difficult for me to do that live in class, but I could try to do that as well. I have notes for it. But I would like you all to work on keygen for a while and make sure you don't have any questions before I send you off into, the weekend. This is your last class of the week, right? Yeah, okay. So take a crack at this and make sure you don't have any questions, and I will either present questions to class or not, depending on what you ask. But here's the stuff going on. I have to go get more water, and I will be right back. Oh, I'm also going to nuke the recording. Am I going to? Yes. Yes. Ooh, I don't know what you're going to ask.